In this video, we're going to talk about rational expressions, including simplifying rational expressions. So let's first talk about a definition for a rational expression. A rational expression is basically a fraction, but in this case, the fraction has polynomials as numerators and denominators. So your formal definition, any expression in the form of P over Q, where P and Q are polynomials, and that should say Q, the denominator Q, is not equal to 0. All right, so we have three examples of rational expressions below. So the polynomials can be anything in the numerator, anything in the denominator. Now, the one thing about rational expressions that we need to be aware of is that there are sometimes values for the variables that can make the expression undefined. So a rational expression is defined as long as the denominator is not equal to 0. If there is a value or values for the variable that make the denominator 0, then we say that those values make the expression undefined. The domain is a set of all values for which the expression is defined. So usually we just start with the real numbers and then delete any of the values that make the expression undefined. Here's an example. So for this expression, we have x minus 5 over x squared minus 4. So if we're looking at the values that make this undefined, we're looking at values that make the denominator 0. In this case, if x is equal to 2 or negative 2, when you square that value and then subtract 4, you will get 0 in the denominator. So the domain would be all real numbers except for 2 and negative 2. Notice that we do not mind at all if the numerator happens to be 0. That's completely fine. Right, so let's take a look at how to simplify rational expressions. In order to simplify rational expressions, we are going to factor completely and then cancel out common factors. So we're going to take a look at the two examples that you see here. All right, so I have these examples written out. So we'll take a look at the first one, where we have 3x minus 12 over x squared minus 16. So we're going to factor as much as possible. And then just like when we have fractions, if we have a common factor in the top and bottom, we can cancel that common factor out. So we see in this case, we can cancel out the x minus 4, and we have left 3 over x plus 4. So again, the factoring methods that were used here in the numerator, there was a GCF, and in the denominator we had difference of 2 squares. When we cancel out these common factors, that really means we're dividing that factor by itself, and when you divide a value by itself, it is equal to 1. So we really multiplied 1 in the numerator and 1 in the denominator, and that just gave us 3 over x plus 4. In the second example, we are going to have to factor the two trinomials. In the numerator, we have a GCF of 4. So we'll factor out that 4 first, and that gives us x squared minus x minus 6. In the denominator, we also have a GCF of 2, so I'll factor that out. That leaves us with x squared minus 2x minus 3, but each of these trinomials needs to be factored further. The leading coefficient is 1 for both of these trinomials, so we can just factor by looking for products that give us the factors that give us the constant as a product and that add to the middle coefficient. Okay, just finishing factoring the denominator. And then we see that we have a common factor of x minus 3 that we can cancel out, and 4 and 2 have a common factor of 2, which leaves a factor of 2 in the numerator. So what we have left is 2 times x plus 2 divided by x plus 1. And in general, let me go back to the end here, you don't have to multiply your values together, your polynomials together. You can just leave them in factored form. And this way it's easier to check to see if you have simplified correctly and that you don't have any more common factors to cancel out.